Hello guys. Hello guys, welcome to Self Help Maths Academy. Today we're going to discuss about the mathematical induction, and let's see how we exactly solve the examples in the mathematical induction and what is this concept is all about. So let's observe first. Now if I have, for example, I'm going to take now 1, I can write it as say 1 square, and I'm writing 1 plus 3 as 2 square. If I want 1 plus 3 plus 5, this we can write it as 3 square. If I am adding 1 plus 3 plus 5 plus 7, then I can write this as 4 square. If you observe carefully, this is nothing but I'm taking the sum of the odd integer here. So 1, then 1 plus 3, then 1 plus 3 plus 5, then 1 plus 3 plus 5 plus 7. And I'm getting here 1 square, 2 square, 3 square, 4 square. So in generally, if I want to add the odd integer, like is the sum of the first n positive odd integer is always equal to n square if you see this way, like 1 square, 2 square, 3 square, 4 square. If I want to add like this 1 plus 3 plus 5 and so on up to n, if n is the that they are all the positive odd integers, is it always equal to n square? In this example, one way of answering this question is by observing that this particular sum is in the arithmetic progression. You can see the difference between any two terms is equal to 2, and then simply you will use the summation formula. Sn is equal to n by 2 and 2a1 plus n minus 1 into d, and then simply you take the first term in any series. You can see here the first term as 1 and the common difference as say 2, and you can take your last term as n here. And if you add all this, if you substitute here the in the formula, it is simply n by 2 2 plus n minus 1 into 2. And if I simplify this, this will become 2 plus 2n minus 2. So here you can see that this 2 cancels, it is simply n square. So this was possible because the given series was arithmetic and we were able to do it with the formula. The next question is it possible that this approach, this particular approach, whatever we are discussed now, is possible only in case if it is arithmetic series or the geometric series. But if the given series is neither of them, then how do we prove the formulas? So then for that, we are going to introduce the method of proof that is called mathematical induction. It is actually used in the wide range of formulas in order to, inputting the formulas, those may not be in series in nature. So therefore, this particular method is basically very essential. Now let's see this particular method. How do we approach to this particular type of problems and this method? Basically, the mathematical induction involves 3 steps. Step number 1 is, in this step we show by direct substitution that the proposed result is true for some value n, usually the smallest. I mean, we prove the result is true for, we prove here the result or the formula is true for, usually for the smallest value, let's say n equal to 1. Then the step number 2, here we assume Here we're not proving, we're assuming that the result is true or the formula is true. The result is true, say for n equal to k. And in the third step, we're going to prove the result is true for n is equal to k plus 1. So finally, in the third step, we are proving again that we prove the result is true for n equal to k plus 1. Okay, so let's see now. So these are the three steps involved in the mathematical induction. The first one is we are going to prove the result is true for n equal to 1. Second one is we assume whether the result is true for n equal to k. And the third step is we prove the result is true for n equal to k plus 1 or not. Now let's see some example. The first one, the simple example we will take first, that summation. The first example is about summation of, say, first natural numbers, n natural numbers. I'm going to take, that is, say, 1 plus 2 plus 3 and so on up to, say, n. Is it equal to half n into n plus 1? So this is what we have to check whether this is, true or not by using the mathematical induction. Let's see how we prove it. As we said, the first step is we have to see whether the result is true for n equal to 1 or not. So step number 1, if I take let n is equal to 1, then you can see here on the left hand side, when n equal to 1, I have to consider only the first term, that is LHS is equal to 1. And then this implies, you say, now for the RHS, wherever n is there, put n, put 1. This will be half 1 into 1 plus 1, which is equal to half into 2, which is again 1. So you can clearly observe here LHS is equal to RHS, that is equal to 1. So this gives us that this given formula or the result is true. This result is true. We can conclude that thus, we say that thus the result is true for n equal to 1. The first step. Now for the second step again, we have to assume that the result is true for n equal to k. So let us assume now in the step number 2, let us assume the result is true for n equal to k. So in this case, I'm going to write this as 1 plus 2 plus 3 and so on. Wherever n is there, I'm going to put k. That will be simply half k into k plus 1. So this is our step number 2. We are assuming that result is true for n equal to k. Now for the step 3, we want to prove whether the formula is true for n equal to k plus 1 or not. So we want to prove the result or the formula is true for n equal to k plus 1. So for that, what I do is, I'll try to write, because we have to, now you see up to k plus 1, and again you're trying to prove it as up to k plus 1. So you're going to write now your result as 1 plus 2 plus 3 k, and the next term will be k plus 1 on the left hand side. Okay, and then On the right hand side, replace k by k plus 1. This will be now k plus 1. This is k plus 1 plus 1. This will become half k plus 1 into k plus 2. That means if you simplify this further, your right hand side will become half. If you multiply this, this is k square, and this is k square here, plus 2k plus k plus 2. So when you simplify, it is simply half k square plus 3k plus 2. So this is actually your RHS. This is what we are getting in the RHS. Now we need to prove that our LHS also is the same. Okay, so let's see. So therefore we need to prove whether LHS is the same or not, because this is the RHS result. If you prove that LHS and RHS are same, then we can say that yes, this is what we wanted to prove. Now if you observe the LHS carefully, here from S2, this result 1 to k is nothing but half k into k plus 1, and then plus you have got here extra term, that is k plus 1. So now if I simplify this particular term on the LHS, if I get this, then I should say that this result is actually true for n equal to k plus 1. Let's do now for the LHS. So for the LHS, I'm going to simplify it separately here in the same manner. You can see. Let us simplify this part. This, if you see the LHS closely, this is equal to, here you have got, you can see here 2 is the LCM. Here it is 1. So I can write this as, let me write it. We will write this as, okay, this is equal to 1 by 2 here. This is k into k plus 1 plus 2 times of k plus 1, because the LCM is 2. Okay, this will give us, if you simplify, this is simply k square plus k plus 2k plus 2 over 2. This is nothing but k square plus 3k plus 2, and here we got 1 by 2. If you observe this result and this result, this is your LHS and this is your RHS. If you see, your LHS and RHS are one another same. So hence what we say is, we conclude here by saying that your LHS is equal to RHS. Therefore, thus the result is true for n equal to k plus 1. If the result is true for n equal to k plus 1, then we have to say that finally the result is true for all the positive integer. I mean, you have to say all the, it is true for all the values of n where n is a positive integer. So this is one example. Now let's see another example. All right. Now, if I have, like, say something like this, 1 plus 5 plus 5 square, and so on up to 5 to the power n minus 1 is equal to 1 over 4 5 to the power n minus 1. Okay. So again, first step number 1, first we need to prove the result is true for n equal to 1. So let us prove the result is true for n equal to 1. Now, if you see on the RHS, you have got n equal to 1 means you have got here LHS is equal to 1. And RHS, wherever n is there, put 1. This will be equal to 1 by 4, 5 to the power 1 minus 1, which is simply 1 by 4, 5 to the power 1 is 5 minus 1, which is 4. So we'll get here 1. Hence, LHS is equal to RHS is equal to 1. Thus, the result is true for, thus, the result is true for n equal to 1. Now, let's go for step number 2. Now, let us assume that the result is true for n equal to k. Now for this, we can write this as 1 plus 5 plus 5 square and so on. Wherever n is there, write k is equal to 1 by 4 into 5 to the power k minus 1. And step number 3 now. We now prove the result is true for n equal to k plus 1. Okay, so let's to prove this, that the n is true for the result is true for n equal to k plus 1. So we have to write first the rewrite the formula for n equal to k plus 1. That is, you write it as 1 plus 5 plus 5 square and so on. You have to see now you are writing it up to k to the power n equal to k plus 1. So the first you will be writing here. First you will be writing it as 5 to the power k minus 1. And the next term is you have to replace your k by k plus 1. So k plus 1 minus 1. This will be equal to, same thing on the right hand side also, replace your k by k plus 1. This is simply 1 by 4, 5 to the power k plus 1 minus 1. Okay. So now we have to check that this particular, we have to show that on the RHS we have got 1 by 4, 5 to the power k plus 1 minus 1. So is it the LHS also is the same? That's what we have to prove. Now to prove that, if you see from S2, this is equal to, from S2, we have, from the second step we have, this is equal to 1 by 4 into 5 to the power k minus 1. Plus this is, now you can see minus 1 plus 1 cancels here. It is simply 5 to the power k. So now let us simplify this particular result. This will be equal to, you can see 4 is the LCM. So this will be 5 to the power k minus 1 plus 4 times of 5 to the power k. This is 4 times of 5 to the power k divided by 4. All right. Now this is equal to, you can observe again here. I have got 5 times to the power k and 4 plus 4 into 5 4 into 5 to the 5 to the power k. This will become 5 times of 5 to the power k minus 1 divided by 4. So this is simply 5 to the power 1 and 5 to the power k. We can write it as 5 to the power k plus 1 minus 1 by 4. So this is as good as this is your LHS and this is your RHS. If you observe both, then your LHS and RHS, they are same. Hence, you can conclude that, hence, the result is true for n equal to k plus 1, and thus you say that thus the result is true for all the positive integer, for all n. Okay, so this is how we'll be proving actually the by mathematical induction. This involves three steps. One is you're going to prove the result is true for n equal to smallest value. So in the examples which we have taken the smallest value as n equal to 1, and then you will be taking assuming that the result is true for n equal to k, and then you will be proving the result is true for n equal to k plus 1. Finally, we should give a conclusion that the result is true for all the values of positive integer. So this is how we're going to solve the example, and some more examples we'll solve it in the next video. Okay, so till then you take care. We'll see you all in the next class, and till then you take care.